Look at any object you consider well-made, and your eye naturally travels along its seams. The hairline where a laptop lid meets its base, or a phone's glass meets the metal frame. We tend to view that empty space as nothing, but that absence, the deliberately engineered nothing between two parts, is a highly considered design feature. The Japanese practice a discipline called kansei engineering. It is the formal process of translating our raw human emotional responses into exact physical design parameters. They know that we judge objects with our feelings before our reason. In a showroom, an uneven gap immediately communicates cheapness. A consistent, tight space reads as a visible hallmark of care and craftsmanship. The empty space between components acts as the ultimate battlefield for perceived quality. It is exactly where the illusion of perfection is either won or lost in the mind of the buyer. When we do spot a misaligned cardboard or an uneven plastic seam, we usually assume it is a factory problem. The conventional wisdom blames the assembly line, assuming a line worker simply had a bad day and failed to align the pieces. The reality is that the width and variance of a seam is virtually never swept up at the end of the line. It is decided years before the factory is ever built. The physical reality of a gap is actually the visible sum of upstream architectural decisions. This schematic of a mechanical part shows us why perfect manufacturing is impossible. Because nothing can be made perfectly, every single part carries a tolerance. That is a strict, mathematically permitted band of variation, governed by a geometric grammar known as ASME Y14.5. When you bolt a dozen individual parts together, their microscopic permitted errors do not cancel out. Engineers run a tolerance stack-up analysis to calculate how these errors compound, vector by vector, as they pass through an assembly. In the early concept phase, designers face a massive financial temptation. They can choose loose tolerances to save immense amounts of money on tooling and parts manufacturing. By choosing loose tolerances, the math guarantees an ugly, wandering gap at final assembly. The catch is that you simply do not see the bill for this decision until the very first physical chassis is put together. Some executives refuse to accept that math. Ferdinand Peake famously demanded gap targets his engineers thought were impossible, forcing them to draw tight shut lines deliberately into the surface geometry, rather than accepting them as unavoidable defects. The most radical concept phase move is to eliminate the gap entirely through a unibody architecture. When Jonathan Ives decided to carve laptops from a single block of aluminum, he replaced multiple parts with one. This mathematically eliminated the plastic gaskets and compounding tolerances that cause uneven gaps in the first place. You cannot have an uneven seam between two panels if there is only one panel. Achieving a perfect seam, or eliminating it completely, is not a downstream manufacturing trick. It is a wildly expensive architectural bet made at the concept stage, executed precisely because the psychological impact of the seam is worth the cost. But when you ignore design for manufacturability, designing early for how a thing is made, those architectural choices will rapidly magnify your microscopic tolerance errors. The Tesla Cybertruck provides a clear example. Its flat, stainless steel faces act like a magnifying glass, making any uneven seam brutally visible. Facing criticism over panel fit, Elon Musk sent an internal email demanding sub-10 micron accuracy and parts that fit like Lego. The tragedy of that email is its timing. You cannot email your way to a tight gap once a product's architecture is frozen. Lego pieces only fit together flawlessly because their interlock was mathematically designed before anything was manufactured. This animated diagram shows how this physical law translates to generative AI. Like a physical assembly, an AI model will naturally drift and compound visual errors downstream unless strict parameters lock the geometry into place from the start. True consistency for professional work cannot be patched over or prompted at the final render. It must be built directly into the software's foundational architecture. The empty space between two parts looks like the last thing anyone designs, but it is in fact among the very first. Design decisions are cheap as a sketch, brutal once tooled. See every angle before you build.